Good morning, everybody, and thanks to the organizer for inviting me. I will speak about the galactic structures measured from the microlensing. So this is a few topics that I will develop in this talk, not in the rigorous order, but so I will first say what is the specific income from the microlensing in the observations on the Milky Way structures, in the study of the Milky Way structures. Then I will show the current status, the current knowledge for each structure. I will insist on some of the difficulties that are related to the galactic structure studies, and then say a few words about the next steps. So the microlensing actors for a microlensing effect belong to several structures in the galaxy. So we have the bulge, we have the bar, we have the central bulge, we have a bar which has an inclination of about 13 degrees, the shape, which the shape is not completely clear now. We have a thin disk, we have possibly a thick disk, also spiral arms which can have some overdensities, and last but not least the halo which host the hidden matter of the hidden galactic matter. So the microlensing observables coming from a single event, from a standard, what I call standard or simple event, which is the point source, pointless, and constant transverse velocity event. It is well known that the information that is given by one single event is just one information, which is the Einstein crossing time, TE. But if you have a collection of events, a series of events, then you can get some statistical information, for example, probability for the microlensing to occur, which you cannot get from a single event. So you get more information from a series of events, and the two basic on which I will insist on the rest of this talk is the optical depth tau and the Einstein duration distribution. So studying these statistical data will help to constrain the total visible plus hidden galactic mass, also constrain the initial mass function of the lenses, and constrain also the relative velocities and the relative kinematics between the observer, the lens, and the source. So I just mentioned briefly the non-standard events because I will not consider them for the statistical studies, but it's just a very minor population and probably much more complicated to extract statistical information from this. So the statistical information that we get from a certain event, I know if I go in more details into the optical depth, this is the probability for a given star, to lie behind an Einstein disk. So the Einstein disk is proportional to the square root of the mass of the lens, then the surface is proportional to the mass of the lens. So if you consider a set of lenses at a given distance, then the optical depth is simply proportional, due to these lenses, is simply proportional to the sum of the mass of the lens, regardless of the composition of the mass function. So it doesn't depend on the mass distribution. Now the other collective information that we get is the distribution of the Einstein ring crossing time, TE. We can use the first moments as the mean of the dispersion of this distribution to compare with the model. A golden way to compare with the model is to make a Kolmogorov-Smirnov test, type test, which helps you to compare the one-dimensional distribution of TE, of Einstein time, and with the expectations. The problem is that this technique cannot be used in multidimensional distributions. So I briefly also mentioned the impact parameter and the time of the maximum duration, which is well known not to provide any physical information on the lens, but it doesn't mean that it is useless. You should always remember that the prior distribution of these parameters has to be flat. And this is something you can check after you have a set of microlensing events to check the signal quality, to be sure that you are not overwhelmed by a parasitic signal, which is not microlensing. Okay, so this is some of the basic formulas that are used for the optical depth estimates. So first, we consider the optical depth to a given distance. So this is, for example, the case for the large or the small Magellanic Cloud optical depth estimates. So this is just the integral up to the distance of the source of the number of lenses that you get from the density of mass and from the volume, and times the Einstein ring surface. So as I said before, this expression simplifies, and you just get an expression which is directly function of the geometry and of the density. Then the point is that the source distance can be widely distributed if you are not looking at LMC or SMC. And an example that for the galactic center is not that clear, but if you look at the galactic arms and the direction which is far from the galactic center, you clearly see here that the population of the red giants is distorted, which means that the red giants, these stars, lie at different distances with respect to us, not at a unique distance. And this is a complication that has to be taken into account when you want to interpret observations with models. Okay, so then that's why we decided also to define the optical depth to a given source population, which is adapted to your catalog. So you have a catalog with a distribution of distance of sources, then you have to adapt this, and this is simply the average optical depth towards all the sources that are entered in your catalog. Then you have to confront this optical depth to the observations. The estimation from the observations is just the way we connect this fraction of solid angle occupied by Einstein rings with the fraction of time during which the source is magnified more than 1.34, which corresponds to the source, the time which is spent by the source inside the Einstein ring. And this is given by this formula. You notice there, just make the sum of the time you sum the time which is spent by the source by the source behind Einstein crossing radius. You have to take into account an efficiency where so you see that will be one of the delicate points of the analysis, and some geometrical factor, and then you have to normalize by the number of observed stars and the total time of observations. Okay, so the main targets that have been monitored since now 27 years already by the different microlensing surveys are first the Magellanic Clouds, the galactic center, and the spiral arms. And this is a brief census of the measurable so directions that have been made to probe the Milky Way structure. First, the galactic center, so all surveys have monitored the galactic center. It has a bright past, bright present, and bright future. No question about this. Now, if you go a little bit farther than the galactic center, if you go a few degrees far from the galactic center, there is only one survey that has monitored the directions far from the galactic center. So we have made in Eros 4 low extinction directions in Eros. So there is also this direction. Some of the directions have already been monitored by the VVV, by the VISTA, but the sampling was not good enough to have interesting results. I think that if we are considering only visible passbands, probably there is a good future for these directions with the use of LSST. But the clear point is that there is an enormous potential to study these directions in infrared, because with the infrared you can be free from extinction, you can see through the dust, you can go deeper, and you have also less problems with the systematics due to the dust. So one of the future is probably connected with the W first. The galactic halo now has been also monitored by Eros, Macho, Ogle, and MOA, and the total time now that has been covered by these four surveys is now more than 27 years. I will say a few words now. about this. I just mentioned briefly the directions toward M31 and also to globular clusters, which are now, well, it's now probably not mature enough to be competitive in this study of the galactic structure. But it's also something promising, especially from space. So the Magellanic Clouds were studied to probe the hidden matter in the galactic halo. So this is a standard exclusion plot that has been obtained by Eros, Macho, and the Ogle. And you read this plot as follows. For example, if you consider the 20% fraction, this is the fraction of halo mass. So if you consider 20% fraction, you cut the point here, you find 10 to the minus 7. You cut the curve here, you find 10 to the 1. And what you can extract from this curve is that the objects, the massive compact objects with masses between 10 to the minus 7 to 10 to the plus 1 solar mass cannot contribute for more than 20% of the total hidden halo mass. Okay, so we have made a game with an internship recently because I was just wondering if we could merge all the databases from all the surveys to have a better sensitivity to the very long timescale events. So the motivation is clear. It comes from the recent discoveries of the gravitational waves, and then I saw that. By the way, I saw in the first seminar on this, I saw this plot of exclusion from Eros, Macho, and Ogle as one of the elements to discuss the result of the gravitational waves. So this triggered me, and for doing such a proposal. So I proposed to this, which is this project, which is called MEMO project. MEMO for Moa, Eros, Macho, Ogle. So pronounce as you like. But so the idea is just to combine the light curves that have been obtained by these surveys. You have different timescales, but you have a common field. And this year you see the preliminary studies showing that this field has been monitored for 27 years. So if you put all the data together, this field, the small field here in orange has been monitored for 25 years, and then 21 years. And this field has been monitored for a total of 16 years. So we made a projection to predict the total number of events with such a joint analysis. And we made a very, very simple or reasonable hypothesis to extrapolate the efficiency of such an analysis. And the first hypothesis is just that if you consider this light curve, and you assume that you multiply by 10 the horizontal scale by the time. So you scale all the times by a factor of 10. It's clear that if you do the same analysis, just multiplying all the time by 10, you will find exactly the same efficiency for these events. Okay? Because you have the same relation between, you have an invariant relation between the Einstein time, between the duration of the experiment and the typical sampling time. So we made this reasonable hypothesis, but we can say that in reality, if we expand this by a factor of 10, we will have more points in the light curve. So the real sampling will be better than this alpha times T sample. So then we can reasonably infer that this should give an upper limit on the efficiency for a joint analysis. So based on this assumption, we have made the following predictions. So this is the expected number of events that we can expect with the combined analysis as a function of the mass. And since the scale here is logarithmic, the dotted point is more than just the sum of the two, fortunately. So there is certainly an interesting potential to merge all the existing database. So you can see that up to 100 solar masses, we can detect a few a few events. We can expect to detect a few events if the halo is completely made of heavy objects, of black holes. On the contrary, if we find no events, then we will have again, we will improve the limit on the dark halo, on the component of the dark baryons to the dark halo. Okay, so that's I have finished for this part for the galactic halo. Now, if we want to understand the galactic structure in the galactic plane, we have monitored the galactic center, and we have also the results to the galactic arms. So now I want to point. It's time to point to some difficulties and to some critical aspects of the Milky Way plane analysis and the Milky Way study when you use microlensing. First, there is one of the first points is the extinction map. So this extinction strongly impacts the distance distribution of the source. So in your catalog. So if you, and this is really a big factor. The problem is that this extinction map, even if it is measured, it has essentially a fractal spatial structure. And also, something which also adds to the complexity is that the relation between the absorption in V, for example, versus the absorption in K is something that depends on the kind of the size of the test. And this is also strongly fluctuating with the position. So all this together makes the potential of W first very interesting, because you would observe in this region where the absorption is much less problematic. Okay, so another aspect is that you expect some degeneracy between the information on the initial mass function for the lens and the kinematics of the lensing system. Just to be brief, a massive lens that goes fast gives the same Einstein duration than the light lens that goes slow. So that's why we have this type of degeneracy. Another difficulty is on the analysis, and the main point here is the detection efficiency control. And the detection efficiency control is really one of the major problems of all the surveys. And we have for example, it has to be averaged on a given source population, red giants, all or bright stars, I don't know. So you see here, for example, for Ogle and Moa, two types of source population. So the efficiency depends on the source population. It depends on the sampling. So that this is clear, this is obvious, but also on the environment. So that's why here you have the distinction between dense environment, medium, and sparse environment. We have to average this efficiency on the impact parameter and on the time of the maximum on the time of the minimum impact parameter to get a function that depends only on the Einstein time. So, but mathematically, if you don't give any precision, mathematically the microlensing detection efficiency is 0, because the gravitation has an infinite range. So I would say in French, I cannot tell this in English. Well, sorry. I stay in English. So virtually every lens has an impact on every source. And what you see is just a finite number. So a finite number divided by something infinite gives you 0, mathematically. Dimension, ouais, de dimension nulle. Dimension nulle dans un espace. Okay, so it's a matter of definition. But by the way, this is just a joke, but it's a matter of definition. So the definition is, the efficiency is typically defined as the ratio of detected events to the generated events. So we have usually the groups use just generate events on standard light curves. So you generate with a uniform impact parameter, typically less than 1, and you generate also the uniform maximum magnitude time during the full observed period. and then you make the average for a given source population. Now you can also make the distinction if you consider your catalog resolved source or not if you use the differential image analysis. In this case, you have to make a special analysis on the content per pixel, number of stars per pixels. Okay, so the hard points are the following. First, the blending. So the blending, which is just the fact that your object in your survey is not a pure star. This impacts first the Paczynski curve shape. It has been shown yesterday by another speaker, and this impacts your reconstructed Einstein duration. So if you say if you don't take this into account in your simulation, then you reconstruct the true TE, but if you are doing the experiment, you do not reconstruct the same TE, and then you do not use the correct, you do not calculate correctly your efficiency. So also the blending changes the effective number of stars that are behind any source that you are monitoring in your catalog. For example, a minor contributor to an object which is part of a detected object in your catalog can emerge with the microlensing, and then it will look like an unexpected microlensing, which is just due to the fact that you have several stars, not only your bright star, which is experiencing microlensing. So this needs careful study to be corrected. And so one of the most powerful way to correct this is to use the image from the space telescopes that will provide the true underlying luminosity function behind each of your objects in your catalog. And also this takes into account the spatial correlations between the blends, because if you generate blends in a flat uniformly in your 2D surface, you will not generate something realistic. So to make a long story short, I just show you this comparison between an Eros dense field and the Hubble Space Telescope, which is slowly appearing here. So that Eros, that's HST, and you see that with this tool of HST image, you can really decompose each of the Eros stars and correct your efficiency calculations. Okay, next hard point is the contribution from non-standard events. If you do if you compute your efficiency, typically you don't take into account the binary systems and all this, which may have a very different efficiency to be detected than standard events. So this is generally not taken into account when estimating the efficiencies, but this can be more or less statistically corrected. Okay, the last point, which is not very often mentioned, is that if you really want to reliably use your efficiency calculation, you need high statistics of events. For example, especially if the efficiency is small, you see that this is in the denominator. So if your efficiency is small for very long time scale events, you can have a very strong contribution from one single event. And then you expect, I would say, worse than Poissonian fluctuations. And also don't forget that this efficiency is an average which has large variations from events to events, which has the same efficiency, with the same Einstein duration. Okay, so this is just a sketch of the monitored fields, of the fields that have been monitored by several surveys. And this is, so now statistics starts to be strong enough to produce 2D optical depth maps. So this is the one from MOA. So here you see that the order of magnitude is between 10 to the minus 7 to 10 to the minus 6. There is no unit, it's just a probability. Then this is I superimpose on this the simulation expectation from the Besançon model. So there is quite a good agreement here when you consider the uncertainties, especially for the optical depth. It's probably more quantitative to consider this optical depth, so to project and consider this optical depth as a function of the latitude only. And then you have a compilation of all the major microlensing surveys during the past 2 decades that are more or less in reasonable agreement. And here you have the fits of MOA, the fit of Eros, which is included in the fit of MOA, and you can see also the Besançon model, which is a little bit at the border, just below, but in contact with the fits, with the observed fits. Okay. One of the points is that there is probably no need for hidden compact object, no need to add some matter in the galactic disk. Okay. Now, if you try to go farther, not just to be confined in the galactic center, you can see you can use the spiral arm results. So this is the geometry, and the four directions, gamma Scuti, beta Scuti, gamma Normae, and theta Musca have been observed for 7 years now, and we have measured optical depth toward these 4 directions. And this is a simple homemade model, and this is the Besançon model, so that are in agreement with this. I have to precise that in these models we have taken into account the distribution, the distance distribution of the sources. But in this plot that so there is no need for massive spiral structure or for a thick disk of hidden compact objects, if you believe this analysis. And then you can, so in this plot, that's the difference is that I show here the optical depth at given distance, but for several distances, just to give you the flavor of the change of the optical depth with the distance. And this is not very often shown, so this is a map versus the longitude that goes as far as -60 to +40 degrees. So now about the mean Einstein durations. So there are maps also published by Ogle, and the small points I think the small points is a model also. I think so. And this is I superimpose here the MOA. So I think that the two experiments, the two surveys are more or less in a reasonable agreement. And this is a prediction by the Besançon model, which probably predicts events a little bit shorter than what is effectively observed. But nothing really dramatic, I think, at this level. So now if you include the spiral arms directions, so that's the four directions here. Here is the expected duration distributions for 4 different initial mass functions. The best fit is obtained, gives very good agreement with the observed mean durations, and the Krupa initial mass function seems a little bit disfavored by this analysis. Okay, so the ingredients that you need for global interpretation with the microlensing, when you use all the directions of the galactic plane, that I suggest to use all the observations. All observations means the color magnitude diagrams that has to be taken into account together with the distributions of Einstein durations and optical depth. So this is, for example, you can describe the color magnitude diagram with mean stellar surface density or with average color, just in 2 points. But you can have more moments if you like, if you have more statistics. This also depends on the statistics. Now, and okay, this is for optical depth. You need an excellent knowledge of your selection effects. What is your effective field? What is the stellar detection efficiency? Or what are the photometric uncertainties and the critical point of microlensing efficiency? So you inject a galactic density model. We played also. We made synthetic color magnitude diagrams using Hipparcos results. Local results, debiased color magnitude diagram. And now you need a stellar luminosity distribution to simulate the source population. You need a stellar mass distribution to simulate the lens population. And this is the different initial mass functions that we have considered in our analysis. And this is also the other critical point is the 3D extinction map. Okay, so this is just an example. So for these 4 parallel arm targets, we did a global fit, and you use our simulation. Sorry, sooner or later it happens. So we use the simulation to connect the physical parameters, those physical parameters, angle of the bar, the mass of the thick disk, hidden mass of the thick disk, and the initial mass function, and we connect this with observables, 4 observables per direction, which is 4 times. So the mean density of the surface density, stellar density, the color, mean color, optical depth, and mean duration. And we minimize the differences between simulation and observed. And we found that it was necessary to adjust, to play with the mapped extinctions, not much, just of 0.1 magnitude in K, but 0.1 magnitude in K makes almost 1 magnitude in V. So we are really extremely sensitive to the control of these extinctions. So we had to assume some systematic and statistical uncertainties on these maps to have a correct fit. So then we obtained these bars, these constraints on the bar from the microlensing. So from the microlensing only, the bar affects essentially the direction of gamma scuti, which is the closest to the bar. The other directions are not sensitive to the bar. So first we saw that we expected a significant distribution in the total, in the mass density along the line of sight. We checked this, we observed this, and we are able to distinguish between a bar at 13 degrees and a bar which is at a very different angle, because this contribution will change a lot. But we are not able to refine the angle of the bar. To go from 14 to 30 degrees, there is no, all right. Okay, we can also distinguish between a short or long bar, but we cannot go into the details with the shape of the bar, specifically because we don't have a lot of statistics. So now about on the disk information, we can get the following information from the microlensing. We can, after you have tuned your model, we get the distance distribution of the sources and of the lenses. So again, we found no need for an hidden contribution. Now about the kinematics, what we realize is that the orbital velocities of the different actors is really dominant over the proper motions. So if we put on or off the ellipsoids of proper motions in the simulation, you essentially do not affect the distribution of the Einstein time in those directions. So now about the IMF, we found that we have some sensitivity to the initial mass function. And that's time to conclude. I think, I just would like to show you something very preliminary. We also try to make an extended map of microlensing expectation in a large domain of longitude, -100 to +100, which is the complete domain of the map of the Marshall extinction map. And then, so this is very preliminary. So with no surprise, you see that the optical depth decreases very fast when you go far from the galactic center. But the interesting thing is that the mean duration of events is much longer if you go at 90 degrees from the galactic center. And this can be, okay, this is what you expect. But this is interesting to see this in a complete simulation. Okay, so W first, that's my last, and then I have a conclusion. So W first should provide an exquisite information for each microlensing event. There's no question about this, but only in a very small field. So I saw that there is in the program there is a possibility to have more fields later, like, oops, sorry, like M31. Okay, my feeling is that there is a very strong potential when you couple these observations, spatial observations, with wide field survey on Earth. First, you can use them to refine the efficiency estimates, as I showed, and so to calibrate the blending corrections, and also you can have a good census of the complex events and to take them into account to correct the efficiencies. So that's time to conclude. So now the microlensing is probably one of the best tools to search for black holes in the plane and also in the hidden, well, visible or hidden in plane or hidden in a halo. Yeah. Now, from the information you can get in the galactic plane, from the microlensing studies in the galactic plane, we can we show that there is no need for hidden compact objects in this plane. The inclination of the bar can be confirmed. We can say something about the initial mass function, also something about the galactic dynamics, but the main sensitivity is really to the orbital velocity. So you can probably refine the orbital model of the galaxy with microlensing in a large domain, in a large zone, in a lot of directions. Okay, and for long-term perspectives, we will certainly need very, very complete studies of absorption map extension models, improve the efficiency estimates, increase the statistics is also one of the major points, and especially through this with the infrared survey. So VVV at Vista would be an excellent, a priori is an excellent survey for this, and then, well, you can consider all these survey for the future or long-term perspectives. Thank you for your attention. Yeah, the over density of the spiral arms probably would not be sensitive, but that's we don't have enough statistics to give firm conclusion on this. We didn't need to add over densities to have a better fit on the model. Possibly the fit would be better, but it would not be significant. So I would wait for more statistics to be more affirmative on this.